Well, let's get used to some elemental composition of pure substances. Woo! Well, there's different ways we look at these things. They're called the empirical formula, simple reduced version, lowest ratio of numbers, 2 to 1, 1 to 1, 3 to 5, can't be reduced any lower. Molecular formula is what it actually is. So that would be your C2H4, your CH4. A lot of organic compounds use this. Molecular formulas are also done and empirical when you have something that's ionic. So just as an example, you got something molecular, right? This can be reduced to its empirical formula. We'll be looking at how we can determine each of these over the next few slides. So, ionic formulas, remember that's a metal and nonmetal, or of course with polyatomic ions. They're always empirical, so that means they are always reduced to its lowest ratio. Covalent formulas, not always. H2O, yep. C2H12O6, I think that's some kind of sugar. Its empirical is lower. And if this is something else I'm not too sure about, maybe a disaccharide, and you can see that is reduced. So it really depends on the type of formula if it's going to be empirical or not. So how do we actually determine an empirical formula? Well, you'd be given the percent composition, like we talked about in the last part, where you have a percent of a compound, that is that. You want to assume that 100-gram sample to make all your numbers easy. Of course, you could have different ratios, but why not make it easy on yourself? Then you use the poem. Percent to mass, mass to moles, divide by small, multiply by whole. It's not a sea chanty, but we'll make it do. And away we go. So this adipic acid contains so much percent of each of these elements by mass. What's the empirical formula? Well, remember, if we have 100 grams of a sample, and again, this is a hypothetical, we would have so many grams of each. Remember, masses are all relatable by moles. So we convert all the grams to moles for each of these. And remember, it's not H2, it's just H. O2 and H2 is when they're in compound form, but these would be separated by element. So then we have a relationship between the different amounts of moles for each of these. So that's the percent to mass, mass to mole. What comes next? Divide by small. So you take the smallest amount to give a 1-to-1 ratio to one of the elements. And you can see I have a 1 for oxygen, about 2.5 for hydrogen, and 1.5 for carbon. This will give you the simplest ratio. Then you want to multiply till whole. So you multiply the values all by the same numbers until you get to something that's whole. It's not always going to be crisp. As you can see, 2.47 becomes 2.5. But you're generally going to have just one of the numbers do that, and the other stuff's going to come out to be great. So the empirical formula of this compound, C3H5O2, would be our empirical compound based upon the percentages given to us. Now, you might see some variations on these things throughout the Pearson practice and so on. But again, those are the things I can't show you every single example that you might see in life. However, you take the same concept and apply it to this. If you have questions, I'm here to go with them. So that was empirical formula. Molecular formula. Find the molar mass of the empirical. That's pretty easy. Multiply and add. Divide by the molecular formula mass by the empirical formula mass. So you're seeing this, what's this ratio between? Multiply empirical formula subscripts by that multiplier found in step 2. No cute rhyme. Not going to hit me up on TikTok for anything. Sorry. So let's take a look. Same adipic acid, right? Let's just kind of work it in reverse. The empirical formula is this. The molecular mass is given. You could also calculate it if need be. What's the molecular formula for this? So I can see that the empirical formula has this molar mass, while the molecular is 146. Divide the big one by the small, you get roughly 2. You usually need to round a bit because, of course, all molar masses are rounded. So I'd multiply times 2, and I get my molecular mass. Molecular mass is either going to be equal to or larger than your empirical mass and empirical formula. Now, if you thought that was easy, good. If not, let me know. Talk through it with me. It does get more complicated, of course, otherwise this wouldn't be AP. So there's what's called combustion analysis. These are when you have things that have carbon, hydrogen, and sometimes oxygen that are burned. And of course, those are going to separate things into carbon, hydrogen, and oxygen in order to determine this. This is a big area of organic chemistry to know how big or what your molecule is consisting of. So take a moment, pause, and read through these things. So I'm going to kind of just quickly go through these, as you might want to jot down some of the main ideas from this, but not word for word. So let's go through this. So again, carbon, hydrogen, oxygen. We have to know the mass of the unknown substance before burning it. This gives us an idea of mass to compare to. You might remember combustion is this hydrocarbon with oxygen making up CO2 and H2O. It's essentially your respiration from biology. Now, if oxygen is part of the unknown compound, which it can be, we usually find the oxygen winds up incorporated into the H2O and CO2. However, we also need to determine how much of the oxygen was used, so we usually use this by subtraction. I'll show you an example coming up. Sometimes it asks you for empirical, and sometimes it asks you for molecular, or for goodness sake, for both. You need two ideas here, though. You need the molar mass to get the molecular formula. Otherwise, we can't use what we just used previously. And you'll have to calculate the empirical first, even if the question doesn't ask for it. This is a nice part, not a nice part, a part that AP likes to utilize is saying, I need this without telling you also need this. So again, doing some of these as practice, getting prepared for these is something you're likely able to see on an FRQ, a free response, not likely to see this too much in a multiple choice. Although they are changing the way they do the multiple choice, giving you more numbers where a calculator may be needed. So I don't know, maybe things will be changing over the next few years. So let's take a look. So here's a brief overview, kind of a general guideline of steps. Why don't you take a moment, read through it, make sure you understand what I'm going to say before I say it, and let's take a look. All right, well, let's take a look here. So you always have CO2 and H2O, and this ratio is the molar mass of carbon divided by the molar mass of CO2. So it's, get those kind of locked down in that ratio. You can always use your periodic table. H2O is always the 2 hydrogen for the total of water. So you would use these to go from your grams of these different components, CO2 and H2O, to seeing how many grams of hydrogen and oxygen you had as your number of moles. Now you got to be careful that you need to use your 1.088 to get your number of grams for the element itself. Once you have your number of grams, because this is H2. Because up above, this gives you your grams of hydrogen, grams of carbon. But when we convert it to moles, remember moles there's 1 mole is 1.088 for hydrogen. So be cautious of that. Most students, that's where they're going to flub it. Now, divide each molar mass by the lowest value. You get your small whole numbers. And again, steps 2 and 3 are needed. Step 1 is required because you have carbon and you need to, instead of a simpler problem where it tells you this, it generally won't tell you that. Finally, this common component is to provide the molecular weight. So therefore, you can take the empirical formula and determine its molecular formula, just like we did on the slides before. So let's take an example. I got one with oxygen and without, and let's see how those go. So let's look at a problem that this would look like for here. So with problem 1, we have the idea of 1.5 grams, some hydrocarbon, meaning hydrogen and carbon only, undergoes complete combustion to produce so much of this here. What's the empirical formula? So again, we can see that we take our amounts of grams of each, use our ratios to get so many grams of carbon and hydrogen in our original compound, and take a moment to look. 1.5 grams, 1.5 grams. That makes sense. Conservation of mass is important in chemistry. Now we use our grams to moles, again using our molar mass of carbon and hydrogen, and again that's just H. We can see we get a ratio here. We can see that when we divide by the lowest number, which is 0.09, I get a 1:3 ratio, which is why it should be here that we can see a 1:3 ratio for what we have. There we go. Don't know why that wouldn't go away. So now we've arrived at the substance of CH3 as our overall amount. This is again far simpler, but we can see that we're given a total mass and we get a whole bunch, which again, your products should be heavier because it's not accounting for all the oxygen that was added in components of that. So let's take out one with oxygen. So you got a small sample. It's got all 3. and we have our two products. Okay, what's the empirical formula? We do the carbon and hydrogen because we know those are consistent with our combustion sample. I can see I get so many grams using our ratio. Now here's the tricky part. This mass does not equal this mass, okay? However, we know that if the rest of this mass is going to be oxygen, so I take my sample, subtracting out what I calculated to get my overall amount of oxygen. And again, should be this plus this plus this equals that. Now I've got masses for all of mine. You've got your carbon, your hydrogen. Remember, oxygen is just 16, not 32. And I get my amount of moles, divide by my smallest, and I get a 1 to 2 to 1 ratio in which the empirical formula is CH2O. All right, so let me know if you got any kind of questions. I'm always here to help. Catch you on the flip side.